So welcome back to the course. So let's have a quick customary review for, let's say, a couple of minutes regarding what we discussed in the previous session, and then we'll move on to the aspects we are going to cover today. So, right, so regarding the review, going back to the slide here, so we looked at calculating delta G, or I guess K, or the equilibrium coefficients at non-standard conditions, right? And then we looked at effect of non-reactants. In that context, we talked about activity of the component, which is equal to the activity coefficient multiply the dimensionless concentration variable. So activity coefficient depends upon the ionic strength, and this variable we looked at how to look at the different units for different phases. So we were done with that. Then we ended up deriving the relevant equation that's represented here for what do we say, calculating the equilibrium coefficient when we have a different temperature rather than the standard temperature. Standard temperature, as we know, is 25 degrees centigrade. So how will the equilibrium change or shift whenever we have a change in temperature? And so same case with pressure, we again derived, or I guess it's a natural corollary. So we looked at that relevant equation. Yes, so we'll move on to the next aspect. So today we are going to start discussing about phase equilibrium now, right? Phase equilibrium. So we are not going to go into it in greater detail, and then we are going to look at a few of the usual examples that we come across in environmental engineering, and then we'll come back to how this relates to delta G, or again as we have here equilibrium, right? So Henry's law, or pardon me, before I go further, so in general we are aware of phases, right? And the three phases that we usually come across are liquid, gaseous, and the solid phases, right? So for example, let's say partitioning of oxygen between the gaseous and liquid, or in this case water or aqueous phases, I guess. So for example, let's say if I get my container, let's say I have a 1 liter container, and I fill it up, or half of it, with wastewater that has DO levels to be equal to almost 0, right? And let's say the wastewater or has less BOD or demand or such, and let's say this particular phase here is just the air, right? And this is at time 0, let's say, yes. So at, let's say, after considerable time, let's say 1 day, let's say, if I come back and measure the waste waters or water's DO, what do you think it's going to be though, the DO now? Is it still going to be 0, or is it going to change though? So in general it would change, depending, obviously we are considering that there is no BOD here, let's say, BOD of your wastewater. So we just assume that there are no organics or compounds that can be oxidized, and that the initial wastewater had no dissolved oxygen, and half a liter of the, or half the sample is filled with air, right? And now again after time equal to 24 hours, we are trying to look at what is the condition of your particular dissolved oxygen, or what is the dissolved oxygen level in your wastewater. So obviously I guess it's going to increase, it's not going to be 0 anymore. So why is that? So let's say there were 5 moles, I guess this is a rough approximation, let's say instead of 5, let's say 8 moles of oxygen in the air there, right? It's not going to be the case, you are going to look at PV equal to nRT and so on. But for example, let's say there are 8x or 8 moles of your oxygen in your air initially, and there are no moles of, or 0 moles of oxygen in your water, because you know that the DO is 0. So what happens after some time, depending on the kind of water or such, there is going to be a partitioning of the molecules, right? So in general, let's say if there are now 5 moles left in your air of oxygen, there will be 3 moles left in your wastewater. So what I am trying to explain is that an equilibrium will be reached after certain time for oxygen between the gaseous phase and the liquid phase, right? So again there is partitioning, or equilibrium has been achieved with respect to oxygen in the gaseous phase. So now earlier where we had 8 moles, we now have only 5 moles, and the other 3 moles are now in the liquid phase, right, or here in this case water. So anyway, this is a very generic approximation, right. I am just trying to paint the picture here for you. So in general, how do we go about it, or how do we look at these aspects, let us say, or how can we quantify them, pardon me. So in general, whenever you want to try to equate the activity of your particular compound in the gaseous phase to the activity of the particular compound in the liquid phase, right, we use, so let us say initially we know that we can say or call this the equilibrium coefficient, but for when we are trying to look at the partitioning between gaseous and liquid phase, we call that the Henry's constant, H, right. So again look at this, this is equilibrium of a particular compound between the gaseous phase and the liquid phase, right, and the ratio here, let us say. So what does this mean? Compound A in the liquid phase is now equilibrating with compound A in the gaseous phase, right. So this is what we see here, and as you know, equilibrium coefficient is the products raised to its stoichiometric coefficient by reactants to its stoichiometric coefficient. So that is what we see here, and again what do we call that here? We call that the Henry's constant. But keep in mind that this is applicable for dilute systems, right. Henry's law is typically applicable for dilute systems. So the same case we can come across, or we come across Raoult's law, and that is applicable to non-dilute systems, right. And what does that give us an idea about? So similarly, though, it gives us an idea about activity of the relevant compound in the gaseous phase is equal to the vapor pressure of the particular compound into activity of the particular compound in the liquid phase, right. And if you want to approximate the activities by concentration, you can do that, assuming that the activity coefficients are small or are equal, right. Activity coefficient in the gas phase are negligible, let us say, right. You can say that is equal to the concentration of the compound in the gaseous phase times vapor pressure into the concentration of the compound in the liquid phase. So same case here too, if the activity coefficients are smaller, obviously this is dilute system, so that is going to be case. You can say the Henry's constant is also equal to what now? The concentration of the compound in the gaseous phase by concentration of the compound in the liquid phase, pardon me, right. So obviously the difference between these two cases is that Henry's law is applicable when it is dilute systems, Raoult's law in non-dilute systems. So what does that mean? I guess again that the key would lie in what we understand by the vapor pressure, and what is that? I guess the vapor pressure is equal to the partial pressure above solution of a pure compound of A. So let us say this is a theoretical value, and you take a pure compound of or pure component of A, and then look at the partial pressure over that particular pure component, you will get the vapor pressure, and that is what this term is here, right. So for example, now to just to try to differentiate here, right, and if we look at a particular example here, where we look at this particular graph where we have mole fraction here on the x axis and the partial pressure on the y axis of particular compound A, and let us say here we have two graphs, let us say, and the other one let us say is this. Please try to take a moment and try to figure out which particular graph, right, would be applicable to which particular law or the system here, which particular graph would be applicable to Henry's law, which particular one would be applicable to Raoult's law. The key obviously is that Henry's law is applicable when it is a dilute systems, right. So what does that mean? In general, the mole fraction of that particular compound is going to be relatively low. So as you see here, that is the particular case here. So here we see the Henry's law applicability, right. And in general for non-dilute systems, and what do we use? We use the Raoult's law, and that is what we see here too, right. Keep this in mind, I guess. In general, most often than not in natural systems we come across Henry's law, but depending upon the kind of system that you use or the engineered system that you use, you can come across the Raoult's law, yes. So, we will move on. I believe the next case would be liquid. So, another example that we can look at is, let us say we have two compounds in two solvents in contact, let us say one case is water. So, we have 1 liter of it, 0.5 liter water, and again 0.5 liter methanol, ethanol or such, let us say, okay. And let us say initially I have a particular compound here, let us think of it as pesticide. Let us say I have again 8 compounds here, 8 moles, pardon me, of a hydrophobic compound here initially at time 0. So, let us say after considerable time I again look at what the system is or analyze the system. What would I see here? Let us say if it is a hydrophobic compound, it does not want to stay in water. So, let us say only 1 mole in water and 7 moles in methanol. So, here we are coming across partitioning of a particular compound between liquid and liquid now, right. So, one widely used metric is going to be the Octenol water partitioning coefficient, KOW, right. It is the concentration of the compound that would stay in equilibrium with octenol partitioned with water. So, example, what does this mean? I guess instead of the methanol example, right, instead of the methanol example, if I have this as octenol, right. So, here if I have octenol, so what does that mean? So, I am going to have relative, let us say known proportion of or equal proportions of water and octenol here, and I am going to put in a known quantity of my particular compound, and after a certain amount of time I am going to look at the number of moles or the concentration of the compound in water and also the concentration of compound in octenol. Then KOW will be concentration of compound in octenol, right, by concentration of compound in water, yes. So, obviously if it is a hydrophobic compound, what does that mean? It would mean concentration of compound in octenol would be high and concentration of compound in the water will be less. So, more or less that means for a hydrophobic compound, obviously the KOW value is going to be higher. But if it is a hydrophilic compound, what does that mean? We know that KOW value is equal to concentration of compound in octenol by concentration of compound in So, for a hydrophilic, and what do we know? So, if it is hydrophilic, it would prefer to stay in the aqueous phase or in water. So, the denominator is going to be higher, the numerator is going to be lesser. So, what does that turn out to be? That means that KOW value is going to be less, right. So, that is what you see for KOW value of hydrophilic compounds typically will be lower, right. So, again this is a approximation that people look at when they are trying to look at is it a hydrophobic compound or hydrophilic compound, and people usually use the octenol water partitioning coefficient, again KOW, and these are standard values available for most of the compounds that you are aware of, let us say, yes. Again, now let us move on to the second aspect, and what is that? I guess here we have fluid solid absorption now. So, many people might be aware of, let us say adsorption based phenomena, let us say, right, and let us see what it is. Adsorption or an ion exchange, let us say. Let us say here I have sites for adsorption, either activated carbon or in a different case ion exchange, let us say. Here I have 5 sites, let us say, right, or for example maybe a better example would be similar to what we had earlier. So, I mean this is a very rough example though, keep in mind that. So, I have a compound, let us say in water, and this let us say is a solid, but not 0.5 differentiation though, I guess. And so, I have a compound here in water. So, more or less I want to know how much of the compound or what fraction of the compound would be adsorbed onto the solid after some time, right. So, I want to know how much of it would be adsorbed onto the solid and how much of it would want to stay in water. So, again there is going to be an equilibrium. So, let us say if a particular compound has higher affinity for the solid, right, then I can say use my what do you say adsorption based process or ion exchange based process. I guess let us just call it adsorption. Ion exchange, it is a relatively different principle though it is under the ambit of adsorption, right. So, if a particular compound wants to stay adsorbed to solid more than it wants to stay in water, so I can go with the adsorption process. So, let us look at some of the usual models that we have. We have the linear isotherm, right, and what is that? I guess Q equal to Kc, right. Again Q is the amount sorbed onto the solid phase by amount of the sorbent, right, amount sorbed onto solid phase, and Qc obviously is your concentration in typically milligram per liter in the aqueous phase or whichever your liquid phase is, right. So, again you can think of K here as an equilibrium constant if you want to, K equal to Q by C is an equilibrium constant, right. So, that you can get from your you can think of it, but that is not the what it is called though. Anyway, Q equal to Kc, what does this give you an idea about? It gives you an idea about the partitioning between solid phase, which is the concentration in Q in the solid phase, how it relates to the concentration of the compound in the aqueous phase or water or solvent and so on. Makes sense hopefully. So, Q is the concentration of the particular compound on the solid phase, C is the concentration of the particular compound in the aqueous phase, and here we have a relationship. But there are obvious drawbacks. It means that as you keep increasing C, it can Q can go to infinity too as C goes to infinity, but that is not the case. So, in general you will have limited number of sites available. So, one model that takes it into account is the Langmuir isotherm, right, and Q equal to Q max. So, this defines the maximum number of sites that are available, let us say Bc by 1 plus Bc, right. C again is obviously the concentration of your compound in water, B is a constant, and Q max is the maximum number of sites available, Q is the amount sorbed by amount of sorbent, right. Again here we have a relationship between concentration of the compound in your solid phase to the concentration of the compound in your aqueous phase. Another isotherm widely used is the Freundlich. I believe this is applicable usually for activated carbon, Q equal to K C 1 by N, right, and again these are all empirical models based on which you can calculate the K and N values, yes. So, again what have we looked at here? We have looked at phase equilibrium, right. We initially looked at what is it now between gas and liquid, then we obviously looked at initially we looked at gas and liquid, then we looked at liquid, and then we looked at fluid and solid. Fluid can mean either a gas or a liquid, right. So, that is what we looked at. So, for example, if I want to calculate the delta G values for these phase changes, what would that be now? And for example, it goes from A goes from phase 1 to phase 2. What does that mean? Let us say, we know that it is equal to delta G is equal to the stoichiometric coefficient into GI bar of your products minus stoichiometric coefficient GI bar of your reactants, right. So, what is that equal to now in this case? So, stoichiometric coefficients are 1, so it more or less means G2 bar minus G1 bar, right. So, Gibbs energy of the particular compound or molar Gibbs energy of the compound in phase 2 minus molar Gibbs energy of the compound in phase 1. So, at equilibrium what does this mean now? Delta G equal to 0, meaning G1 bar is equal to G2 bar, right. So, what does that mean now? The molar Gibbs energy of the particular compound in both the phases will be the same when the system is at equilibrium, yes. So, this is how you link it to what we have been talking about in the previous classes. So, moving on, let us see what we have next. So, we are going to look at an example, but I believe it would be better if I talk about it in the context of what we have here, chemical equilibrium model, I guess. So, we have thus far been looking at delta G values or K values, ion activity product and so on, looking at feasibility and so on, right. This is what we have been looking at, standard conditions, non-standard conditions and so on, yes. But now let us say I want to now step into the those aspects or talk about those aspects where I want to know the concentrations at equilibrium. I want to be able to calculate that, let us say, right. How do I calculate the concentrations at equilibrium now? So, for this particular aspect, let us say there are different models, and in general obviously your particular system is that your concentrations or your unknowns are typically equal to your concentration. So, let us look at that. I guess I believe I have a small example here, right. So, take a few moments to work this out. So, let us say initially I have a particular volume of water, right, and concentration of a particular compound in water initially, and then also it is in going to be what do we say exposed to a volume of gas and concentration of the particular compound in the gas initially. This is at time equal to 0, and after time t I want to be able to calculate what are my concentrations at equilibrium, let us see, right. So, I want to calculate concentration of compound in water, concentration of the compound in the gaseous phase. What are these two unknowns now? So, to simplify the particular example, we are going to assume that there is no compound present in the gaseous phase initially. So, please take maybe a few seconds 20 to 30 seconds and see how you can work this out, I guess. In the meantime, I am just going to list some of the variables and such that we are going to have to calculate known values and so on, but please try to calculate that, I guess, right. So, okay. So, let us look at how to go about this, I guess. So, here we have two unknowns, right, concentration of water in the concentration of compound, pardon me, in the water or aqueous phase, and concentration of compound in the gaseous phase at equilibrium. Obviously, these two are at equilibrium obviously after the system has reached equilibrium, let us see, right. So, the key lies there. So, the system is at equilibrium. So, that is one case though. So, obviously we need to be able to develop two equations, two independent equations, I guess. So, what are those two equations that we can think of now? So, the first aspect that we always look at is the mass balance. So, mass is always conserved. The first aspect is mass balance, right. So, let us look at how we are going to look at that. So, what does this mean? It means that the total number of moles of the compound initially is equal to the number of moles of the compound at equilibrium, right. So, whatever is happening is the moles from water might either move to gas or vice versa and so on, but the total moles is constant, right. So, what does that end up meaning, I guess. So, the volume of water into concentration of water, pardon me, not concentration of water, but the concentration of the compound in water initially plus volume of gas into concentration of the particular compound in the gaseous phase initially. So, I mean assuming that we can convert the units into the relevant units, I guess, will be equal to the concentration of or volume of water into concentration of water, concentration of the compound at equilibrium in water, right, plus volume of gas into concentration of the compound at equilibrium at gaseous phase. So, let me write that down because I have been misspelling that. Right, this is what we have. So, this is a mass balance, right. So, more or less we are equating the total mass before equilibrium to the mass after equilibrium, right, initially and after equilibrium. So, that is the mass balance here. It is a simple mass balance, there are going to be variations obviously, we are going to cover that later on, right. So, here what are the known values? So, we know again concentration of the compound in water initially, that is something we know. We know the volume of water, we know the volume of gas, we know that this particular variable, or there is no compound in the gaseous phase initially. So, we are still left with two unknowns, right, and one equation. So, thus what are we missing here? So, we need one other equation here, right, to be able to solve that. So, obviously the key is that this is a equilibrium model, right. So, the equilibrium between the gaseous and the aqueous phase, that is something we need to consider. And what is that, I guess here? And we know that the Henry's law or the Henry's constant is going to give us the what do we say, ratio of activity of the compound in the gaseous phase, right, in the gaseous phase let us say to the liquid phase, right. So, if I am going to use what do we say, the concentration or approximate that by concentration. So, that is going to be equal to concentration in the gaseous phase by the concentration in the aqueous phase at equilibrium. So, now I have two equations, right, and two unknowns, and with that I can, or I will be able to solve the relevant system here. So, what are we looking for here always, I guess, right? You are trying to identify the unknowns or the variables and obviously develop relevant equations to be able to solve them. In general, widely used equations in our particular system or environmental engineering, what are they going to be? They are going to be mass balance, right, typically mass balance almost always. And what else can we look at? We can look at charge balance, right, again that is something people miss. So, maybe we will have that in the homework, one example problem on charge balance. The charge needs to be balanced, no particular solution will be charged, right. So, what else now? And then the equilibrium models or equilibrium balance models. So, these are some aspects that we are going to look at. So, obviously here we have looked at a generic example now, right, but this is not going to work every time though. So, how can I go about it? Let us say here I have an example, but before I go further I believe I need to talk about some other aspects here, right. So, let us look at that, let us see. So, now let us say we have acetic acid in solution. Let us say, or let us say I have a beaker of water and let us say I am putting in acetic acid in this particular solution, and I know the concentration of this particular acetic acid initially, and I am putting that up in here. We are talking about a very simple model here, and I want to be able to calculate the pH of this particular solution once the acetic acid has been what do we say, added to the solution, and pH is minus log activity, again it is activity of H plus. It gives us an idea about the concentration or activity of H plus in solution, which people approximate by minus log concentration of H plus, right. pH is the negative logarithm of activity of H plus. Now, how do I go about this now? So, there are different ways. So, let us look at one way that people can consider. Let us say yes, CH3 CO and OH, right. So, this is acetic acid CH3COOH, right. So, it can behave as an acid and dissociate or try to donate the proton H plus. So, this can exist in or will exist in equilibrium with the deprotonated form CH3COO minus. This is the protonated form because it has the proton, and this is the deprotonated form, right. So, this is what you see here, yes, and this is some background information. Obviously, we are going to look at this in greater detail in our section related to the acids and bases. Anyway, this is one particular example, but I am still trying to calculate the pH of my solution, and I only know the initial concentration of the acetic acid that I put into my solution, right. So, I am going to approximate or use the nomenclature HAAC to what do we say, approximate CH3COOH. So, right, HAAC is nothing but CH3COOH in my what do we say, nomenclature here. So, as we know HAAC can be in equilibrium with AC minus or acetate ion and H plus. Yes, how do I calculate this now? What am I missing or how do I go about it? So there are different ways, right? So one aspect certainly that you can consider is something that would stay constant now, right? So people would in general look at total acid, right? And total acid is something I will decide as not total acid, pardon me. Yes, let us go with total acid or total acetate. Total acid will be HAC plus AC minus. So the total acid that I add initially is going to be in either of these forms, right? Yes, the HAC naught that I add initially is going to be in the form of either HAC or AC minus, and so this is like an equation, an additional equation, and I can use that with the other equilibrium models that I have. For example, for this equation I will have a K value, equilibrium constant value, right, or acid dissociation constant, and I will be able to solve the system, right. This is one way to go about this chemical equilibrium model, yes. But the issue here is that if I have any other compound, let us say, that can form a complex with acetate, let us say Ca2 plus, let us say, right, that will then interfere with this equation. No more will your total acid equation be valid. So how do we go about this, right? So you want to develop a generic equation, not generic equation, pardon me, a generic approach that will suit all the needs, right, all your needs. So that is what we are going to discuss in our next class. So with that I will end today's session, and thank you.